High performance design. We need better buildings. I'm Scott Bowman. I'm the owner of Integrated Design Energy Advisors, otherwise known as Idea BuildWorks. This particular presentation was given to a class of WAUKEE CAPS students, which is for the Center for Advanced Professional Studies. These students particularly were looking at engineering, but also included those interested in architecture and other aspects of the built environment. Also, the video production you're about to see was done by another strand of the CAPS program, the Business Technology and Communications. So this is really a totally student developed after these first few slides, and these students were such a pleasure to work with, and frankly our future can be in good hands with these kids. High performance is where we need to go in the built environment. This presentation is a foundational piece of what I want to do as a message to any group, much less design professionals. And it really goes into some of the reasons that I formed Idea BuildWorks and Idea, and why and what the process is to get to high performance. So hopefully you'll enjoy this, and this is the kind of presentation that can be given to just about any group with some modification in order to introduce the idea of high performance and sustainability in the built environment. I took this last night of one of these bins with the brick in it. I think this is now going to be in every presentation I do. So what is my passion? My passion is sustainability and something that I call high performance buildings. And we need better buildings. So what are the pressures? Why do we need high performance? One of them is our buildings use a lot of energy. Over 40% of primary energy. So if you look at all the energy used for all the different sectors, transportation included, 40% of that energy goes to buildings. Over 70% of the electricity we use is used by buildings. So even though when we generate electricity, one of the largest contributors to greenhouse gas is coal. So that is one of those areas. It means 40% of the CO2 emissions, and it's using almost 13–14% of the potable water. And if you look at the worldwide supply of water, only 1% of the water on the planet is available and is fresh. Everything else is either salt water or used in some other manner. So buildings are the largest by sector of the CO2 emitted, primarily because of the generation of electricity. So why do I like green buildings? Why do I like high performance buildings? Well, it's been demonstrated we can use anywhere from 24 to 50% better, less energy. The CO2 emissions, because often we're using some renewables, we can reduce even up to 40%. Water use, it's fairly easy to get to 40% less water use in buildings. And solid waste, which sometimes we forget that our landfills are starting to fill up, can be reduced by 70%. Also, people are healthier. And I'll show you some of the things that both save energy and create a better environment, someplace you want to work. Many of those things are actually demonstrated here in this building. Our codes are changing. So this is, in 1975, we had the first energy code, and they just set that at 100. It's just an arbitrary number based on average energy use across the country, across all segments. Well, you can see over the years we've gone down. We had one blip where it actually used more energy, but then it's been pushing down. The Department of Energy challenged ASHRAE, which is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. It's a mouthful, I know, but only engineers would have that complex. But you'll see they challenged that we had to be better, 30% better. So ASHRAE 2010 took us down to really pretty close to 55% of what we used in 1975. And the code that will probably be adopted next year in Iowa and most of the rest of the country is getting us to 50%. So as design professionals, if you pursue this as an architect or an engineer, you're probably going to be significantly below this. And in fact, there is the 2030 challenge, which is saying by 2030 we would be net zero. In other words, our buildings produce as much energy as they consume. But this is the real story. This is CO2 for 6,500. Anybody know how we get those numbers? How they get that data that far back? It's basically archaeology. You start to see this in the environment, in the fossil record, then into tree rings, and you get this information. So this is verifiable. Look at what's happened. Basically, we have gone up a significant amount just in the last 60 years. But what happened in the last 50,000 years? Us. We happened. And regardless of whether this is man-made or not, the response is the same. If you are in a hole, you don't dig the hole deeper. So what does high performance, how do we get to high performance? And I have a fairly simple formula. First, you have to use less. Now, even though I'm an engineer and I get to do stuff, I am the #1 proponent for architects to have better envelopes, even though that means I get to do less. So we need to reduce that load because, frankly, once you determine the envelope, you have the fixed cost for the rest of the life of that building. Because think about the 100-year-old buildings. Think about the 50-year-old buildings. Think about the 30-year-old buildings that still have single pane glass and may not even have insulation in the walls. So once you set this envelope, you're done. Then you get into my stuff. As an engineer, I need to use that energy that's required efficiently. So system selection, the type of way I heat and cool it, the equipment I use, how I light it, the controls I use. But there's a key one right there. Behavior and use. The older I get, the more I wish I had not skipped my psychology class and I used creative writing instead as my alternate. Because I found out I need to be a social scientist. Because technology can only take us so far. And almost all the technologies that I use to reduce energy can be defeated easily. So if the users don't change their behavior, it doesn't matter what we do as design professionals. They will use the building and they can use more energy than I ever expected. Then make it on site. Too often, people symbolize sustainability by putting solar on it. And I'm old enough that I had a colleague come back to me and said 10 years ago when I started talking about sustainability and LEED, which is leadership in energy and environmental design, that I said, don't just put PV on a bad building, because all that means is you're going to waste energy really, really efficiently. So you can't make up for a bad building. You have to attack these two areas. And to make that happen, I do a whole presentation on what's called integrated design. And all integrated design is getting architects and engineers to talk to each other at the very beginning of the project and listen to each other. I'm going to talk a little bit about energy modeling because it's really, really close to a humongous, complicated video game. And it's the foundation of being able to do anything better with our buildings. So what we do with energy modeling, it's a very complex program where we take into account everything associated with the building. So we look at the people in the building, how active they are, what their clothing is. We look at the heat that comes from monitors and computers and equipment and lights. We look at the heat that's transferred through the wall, the solar energy that comes through the window, the infiltration that happens in the building, which is just uncontrolled air that leaks into the building, what the ground does, what happens at the roof, what the system's doing. It takes into account everything associated with the operation of that building. There are hundreds and hundreds of inputs into this. Then the calculations are done hour by hour using 10-year average weather. It takes the sun angles and the intensity for each of those hours. And yes, that means 8,760 calculations. Individual, discrete calculations. But that's only the start. For each hour, there are actually hundreds of calculations. First of all, you have to figure out what's thermal, what's coming into it from outside, what's the solar, if there's any shading, has it shaded the building, and then what's our internal gain against what time of day it is. Then it's the mass. So if you have mass in a building, which is just like, if you think about a older, like the, have you been in the City Hall? The Des Moines City Hall. The Capitol building is a good example. That is a massive building. Some of those walls at the bottom can be 4 feet thick, because that's how they built structure back then. Well, if you heat that structure up, it can take up to 24 hours for the heat that hits the surface to make it to the interior. It can at least take 12 hours. So you have to know, has the heat that hit at that point even gotten into the space yet? Then it looks at what is coming from that previous hour. It looks at what systems we have, how much water, air, whatever we're using to heat or cool the space. And then it determines the energy that's required. Then finally, it goes back to what's the efficiency of what that is that cools it, what that is that heats it. And it does this. Basically, thank God for computers. But computers junk in, junk out. So you have to have a fundamental understanding of the physics involved, and that's what you get as young professionals as you go into college. You're learning that foundation. I like to say to be an engineer, you don't have to love math and science. Those are paths to doing what you like to do, which if you're an architect, that means designing. If you're an engineer, it means solving problems. But you get calculus and pre-calc and all that, and you know what? You go through thermal, heat transfer, you use all this math, and you end up with a formula that you can do on a 4-function calculator. But if you don't know where it came from, you don't know what effect it'll have. So math and science, for me, was something to get past, to do what I wanted to do. I happened to be okay at it, but I would say I was competent. I was not passionate about math and science. So you change one impact. Let's just change the lighting. So let's say we had inefficient lighting. We now put efficient lighting in. Lighting as a byproduct puts out heat. Well, now that heat's not there anymore. You might just have raised your heating requirement by 10%. It's a system. What if you just put that, I'm sure your parents are saying, why don't you put the thermostat down 1 degree? Of course, in my house, I'm the one that wants to be warm, so I'm always putting it up 1 degree. That could cause the heating to drop 10%, just the set point. Who has control of the set point? That is a question. You do. Does the engineer have any impact on that? Does the engineer come every day to your building and say you've got the thermostat set too high or too low? This is what the results are and why energy modeling is so important. This is an actual building. So the white group is a energy modeling company. This is the code use. You just can't quite see the limits of it. But if you look at heating, cooling, fans and pumps, lighting, plug load, what you plug into the wall, and then domestic hot water. So this is what a code compliant building, and it would use 72.5. I'm not going to go into kBTUs, but let's just say it's a measure, it's a number. The higher the number, the more energy. This was how we designed the building. And it actually used about 50% less than code. You notice we pushed heating and cooling way, way down. This happened to be a geothermal, so we're using the ground as our heat sink. But what happens is we start to get into, well, plug load. Basically, it's the same number, but now it makes up 42% of the load of the building. So that's the stuff that gets plugged into the wall. Again, who plugs stuff into the wall? You do. Does the engineer get to come in and start pulling plugs? No, we don't. So we have the least control. But notice that fans and pumps came up. So sometimes it's a whack-a-mole game. We just spend all our time beating down the thing that just popped up. That's why we do energy modeling. Otherwise, we wouldn't know what those numbers are. Well, this is how it's actually performing. This is after 2 years. I am a little worried that they don't wash their hands.
Is the plug load change because of behavior? Is that why they saw?
Absolutely. It's behavior. I do a lot of presentations with the design team on this particular project, and the owner bought a fake badge. And when she's doing the presentation, she takes out the badge and says, "I'm the plug load cop." But they all agreed to it. All the users agreed to it. So it's a self-policing deal. Now, what it's actually doing with the PV on it, it's saving almost 77% from what it can do. That is what energy modeling helps you to get to.
Do you know what PV is? You mentioned it.
Photovoltaics, sorry.
Which is kind of the solar.
Now, enough of the math. Now I get to show you pretty pictures. All of them come from BNIM, a great partner, a young architect by the name of Carrie Nagel, who I've done a lot of presentations with, and we worked on the building together. And Carrie and I became great friends, even though we're like 30 years apart or something in age. But this is the IUB OCA, Iowa Utility Board Office of Consumer Advocate. It's a very interesting organization that they have to, by code, be in the same building. And yet, they're adversarial. So if the utility board wants to change a rate for a utility, the Office of Consumer Advocate testifies against it. So it's but they have to be in the same building. So they decided to build a new building. It's on the Capitol complex. Well, the building, our design, was 28 kBTUs per square foot per year. It was the energy number that we had to meet, which represented a 60% reduction. And then, yeah, we wanted LEED Platinum, the highest, most sustainable type of building under the Leadership for Energy and Environmental Design. It's a standard we use to measure sustainability. This is what you see from the highway. Again, it's not a small building. It's 50,000 square feet, and it wasn't that expensive. It was about $200 a square foot, which normally this kind of office space would have been $300 a square foot if it had been a commercial Class A office building. It's got a fabulous site. It has the view of the Capitol. You'll see a couple pictures of You can see the Capitol from the inside atrium of the building. So one of the things is, this is the site, and we'll talk a little bit about why that shape came up as we go. But this just gives you some data. And Joe, what I'll do is I'll make sure that you've got this presentation, a PDF of it, and you can share it and use it. Hi, Mike. So, ground floor plan. What happens is, in order to get the energy pushed down, what is a free source of light? Daylight. So if we can use more daylight, we can turn lights off. And I know they're doing that here. If we can turn lights off, we save energy. The best way to save energy is turn something off. So it's oriented to be east-west, because east and west has the worst sunlight and the highest glare, because the sun's really, really low. But on the south and the north, we get great daylight. And we can actually penetrate a building somewhere around 25 feet. We can get daylight from a window 25 feet in. So you start to see buildings that are oriented east-west with a narrow floor plate. This one happens to be just roughly at about 40 feet, 45 feet. You'll also notice that they put these are the common areas, and these are is the open office area for the lower floor. But when you get to the upper floor, you'll see that all the private offices are on the north. So they're maintaining the most daylight for those people that are in the open office. Again, to improve their environment, get more daylight. This is the view of the coming from the south. I'll talk a little more about what that sunscreen is. This is a little better view. This is much greener now. It's going to be a green wall. And it actually is going to be cooler because of that, because of the evaporation of water that comes from the plants. And it's come up, and I know that actually a bird's nest, it's up in about here now. There was a bird's nest this last year, and you could see it from the glass. And so they got to watch the bird and all of that. They do kind of get rid of the wasp nests, which do occur. But this is the monumental stair as you walk in. Does anybody see the elevators? Actually, you really have to look for them. They're way behind back in here. So when you walk in, this is what you see. That's kind of a health issue that says use the stairs, not the elevator. And I see it. I've been there a lot of times, and they're always using this stair. Yes. This is what it looks like from on top, this great gathering area. This is where they hold their hearings. So they have that hearing room, but they've made it very flexible so that they can actually separate the space. They have blinds on all these windows. They still control the lights. You'll notice the lights are off because there's enough daylight coming in. This is a very, very comfortable space. This is the upper story walkway. You'll see how light it is. I'll tell you a little bit more about why those are on and that isn't on a later slide. But you'll see that there's a lot of glass. It's very open, very fresh. It's just a great place to work. This is what it looks like on each corridor, and this is different glass than the other glass. It's much higher performing, but they wanted that place where you could stand and have a much better connection to the environment. This is a nice view of the workstations. You'll notice that the workstations were optimized to get the light in, so these are translucent. Now, IUB and OCA are different people. The OCA decided they wanted this frit, and they wanted it more opaque. Well, the IUBs are pretty much clear glass because it just allows much more light through. These are the offices of the Iowa Utility Board, so these are appointed by the governor. One thing that Kerry talks about, remember when he talked about constraints? Kerry had 63 square feet of glass that he could put in this room. He never complained. He saw that as an opportunity, so he put this high glass to get that light in as far as it could, and into the corridor as well, on the other side of the door, but then gave this nice view if they're having a meeting at the table, or if they're working at their desk, they have light next door. So again, he never saw this as something that was limiting him. He just saw it as an opportunity, and he could do this. We also evaluated, there's a sill here, and Kerry wanted to move that sill. It was at 48 inches, and he wanted to move it down to 42 inches. In most projects, he just would have changed the drawings. In this project, we ran an energy model, and we determined, and we actually improved the glass someplace else, and he got his extra 4 inches. He had a good reason for it. He had a very good design issue that he wanted to solve with that, but it was part of the decision-making process and the collaboration that goes on when you want to build a high-performance building. This is the view from the north. So these are the private offices, and notice that we've got a nice shade. You don't really need it so much on the north, but you notice they're still getting a shading effect. I do have a funny story about a daylit building that was built several years ago, and normally you don't need to put blinds on the north side of a building, but it kind of had a swale out of that. It was almost a walkout on the south. Well, the north had 2 stories exposed with kind of a hill. The hill got covered with snow, and they were getting glare off the snow. So we had to put blinds on the north side of a building. This is the sunscreen, and I'm going to talk a little more. I've got some slides on that. But this was a tool to keep the energy out of the building when you don't want it, and the daylight in when you needed it. So we did some water strategies. There's actually a huge parking lot right here. This building absorbs all of that stormwater, treats it through bioswales and different mechanisms, so there isn't a concrete pipe going to the river. This takes care of all of its own water. It doesn't have to have a pipe. And again, civil engineers got to put less stuff in. Landscape architects got to work really hard on this to make that work. And it treats, can you imagine what comes off, the salts, the oils, all that? That's captured in these bioswales. So it actually treats that water before it goes into the groundwater. So it used 46% less water. 30% of the rainwater from a 2-year event was captured and treated because of this multiple acres. And then 100% of the stormwater was treated. This kind of shows you that the east-west has very, very little glass in it. These are really corridors. So they wanted a little bit of light into them, but you'll notice it's fritted so that we don't get glare. So they treated every surface differently in order to optimize the light and reduce the heat load. So the envelope, one of the things they did was to make sure that it was completely encapsulated and that the line of insulation had no thermal bridging. Thermal bridging, if you've ever seen frost on a window sill, that's a thermal bridge. That means there's some kind of leak there and the humidity in the air has condensed and frozen. So it's a bad building that has ice on the windowsills. We also designed the building such that you could open the windows. That's one of their control strategies. Now, if they open the window, the system knows about it, and it shuts off the air conditioning or the heating. Every worker has an email. If it's nice out, they have a weather station on the building. If it's nice out, they'll get an email. And the email says, you might consider opening the windows. It's nice out. Conversely, if all of a sudden it starts to dive in temperature or it gets real hot, you'll get an email. Please close the windows. And then if they don't close the windows, they'll get another email because it knows the window's open. So, lighting was a huge issue for this building, daylighting. Over 53% of the space is within 15% of an operable window. And 100% have access to that. Some of the other strategies we had photovoltaics to make electricity. We used solar tubes, which are basically a tube that takes light in at the top and pulls it down through the building, one story usually, and it gets daylight into interior spaces. So these indoor, interior conference rooms actually got daylight. The PV is actually providing almost 20% of the energy requirement for this building. And they could double it easily. This is only on one of the roofs. So daylighting, the biggest feature on this building is this sunscreen. And every single blade has been designed that when it is the warmest out, it's bouncing light in, but it's keeping incident light or glare light from coming into the space. So every single one of those blades has a specific angle that it was designed to be at in order to optimize that going into the building. So you can see those blades and how they're fixed, and this was the methodology of how light goes through that. Carrie spent a lot of time, and yet this was fairly economical because they didn't move. They do need to evict birds every so often. But it's very easy to get at. They can actually maintain it. You see the grate there? That's for people to go up and clean the windows. So they actually don't need to use cables or anything. They can get up on that walkway. And then there's strips of fabric because when it is coming way out of the east or way out of the west, we need to get rid of that glare. And so it has those verticals. This just shows the different lighting sources we've got through the building, all efficient. Most of these are not LED because light emitting diode lighting, but that's what's coming. I think if this building was done today, it'd have much more of that in it. This is just a comparison. That is the solar tube, and we turned on the light to show how much light we're getting, and it's just as much as we're getting out of the light fixture. So under normal control in this room, that light would normally be off, but we did this as more of a demonstration. This is just a view of how nice it is going down to the corridor. One other reason that we'd like to separate that first level of cubicles is this is a buffer zone. We don't have to worry about the temperature as much here. We're concerned about the comfort here. So what did this allow us to do? Well, we were able to do 100% of the stormwater that hit the site. We reduced the water by almost 50%. We're well into the 77% on energy. We reduced the construction waste by almost 80–90%. And we've got daylight and views of almost 98% of the spaces. What that translates to is LEED Platinum, the highest level. There are only, I think there's only about 4 or 5 in the state of Iowa. There's only a couple hundred in the world, basically. There's less than 8% of LEED buildings are platinum. So it's the very highest level. So with that, that's my prepared remarks.
Does anybody have any questions or things you've always wanted to ask an engineer but were afraid to ask because we might answer? Sure.
About the windows and stuff, I know you talked about kind of shading, but me and Jake are working on a software called Sapphira, and it kind of runs through how the glazing of the glass kind of fits in with the heating and cooling. So I don't know if you could talk more about that.
Sure. Sapphira is a really good energy modeling tool. I call it a parametric tool that you use early in design. It can tell you very quickly some of those big answers to the shape of the building, the kind of external shades you might put on it, you know, any light shelves that you might have to bounce light farther in, all those kinds of things. It's not very good on systems, so be real careful about it. It's a great way to make these envelope decisions, but then you have to prove it with a much better energy model or a more sophisticated model. But what you're seeing is that interplay. If we have more glass, that means more heating and more cooling, but it offsets electrical lighting and reduces that number. But it also can increase heating because we don't have the heat from the lights. So everything is a balance. If you can reduce how much light comes in to an area that you can't control and move it to a place you can control it, bouncing it in, that means you're really optimizing that glass. You do not need 50% window to wall ratio. That's what we use as a very quick measure to know that efficiency. James will get, you know, I'm often pushing back on architects that 40%, you don't need 40% either. There's a sweet spot between 25 to 35 that can get good daylighting but very good thermal performance as well. It's one of those constraints I like to put on my architectural partners, but I think they should look at it as an opportunity. So that's why when you looked at this building, how different every single piece of glass is. I think there's 7 different kinds of glass on this building. And it all was depending on, did it need to be clear to try and get that daylight farther in? Well, those are the higher ones because we don't worry as much about the glare that's coming from those. But the lower ones will have much more shading. I think they even have some tint in those because that's more glare than it is productive. And then it has higher performance values. So it's a huge balancing act. But if we aren't doing it before they're detailing stuff, then the costs go through the roof. To add things to an overall design is very, very difficult. So that's why Sapphira is a great tool early because it does things very, very quickly. So you get that feedback. But I would tend not to make humongous decisions using Sapphira. It's more to get you on the right path to what the right decision would be. Joe.
I thought it was really neat, probably the first time I saw the systems kind of coaching some of the behaviors when the windows are dictating, it's nice out, open me. Do you see a change in some of the designs and planning from that aspect? I mean, a lot of times on TV they kind of sensationalize the ability to control things from your smartphone when it comes to energy use and consumption.
Like Nest. I mean,
And this is just the opposite. It's these facilities communicating to the people using them. Can you speak to if that is new, or is that changing or evolving? Do you know?
No, it's definitely evolving. In this particular instance, remember that energy chart that showed that the plug load that we were projecting, and that wasn't a guess. That was based on what they were using in their current facility, you know, kind of per occupant or per user. In order to get to that number, there's only about 20% of the outlets in the building have power 24/7. Almost every other outlet has some kind of control on it. Either a schedule, it's only on from 8 till 5, or it's only on if somebody's sitting in the chair in their cubicle. So that the policing comes down to, they don't allow personal fans, they don't allow personal heaters, you're not even allowed a clock radio. They do call it, it's kidding, I didn't include in this present, but we have a BYOB, which is bring your own batteries. So if they have a clock radio that's battery powered, you can use it. So those are some of the things that you have to do. It's a behavior change that has to happen. But the building communicating back to the users, that's fairly new, but it's really in buildings that use natural ventilation or the ability to open windows, that's almost becoming the norm.
Capturing some of that baseline data, I don't know if Noah was in on this last semester, but how old are you for it? Is that something you're familiar with?
Yes.
Is that something they use to collect information on usability, I guess, if it's public?
At IUB, we know all the circuits that have plugs, and we know what that energy use is. So we actually know that was the actual plug load, but we designed the building that way so that we could know what the energy was used for plug load. And that has allowed them to optimize it. One of the changes they've made this year is they were cleaning during the day, but it was very disruptive. So this year, they're actually going to clean at night, but they're asking the cleaning crew to clean in zones. So do all the cleaning, turn the lights out, go to the next zone, and she's going to see where it comes out. And over the year to see if that has increased their energy use dramatically. So, you know, that is one of the tools that this is a real learning building that we continue to work with them all the time on different aspects and different controls.
I thought you were going to go to night vision goggles there for the cleaning crew. Not quite there yet.
No, but you know, daylight cleaning is becoming much more, and I don't know, I was also involved in Project Home Base, which is on University, the large Wells Fargo building, and it just irks me to no end. I drive by it at 9 o'clock at night and every single light is on in that building, and I know it's cleaning crew. There is actually an urban legend. I haven't met the person, but we call it the cat story, that their energy use was higher for lighting, and they determined that the company cat was having too much fun at night and was kind of figured out that he could run through a space and turn the lights on and turned it into a game. And so they adjusted the sensitivity. I think it's an urban legend, but it's a cute story. Any other questions? Well, great. Well, Joe has my email. So if you have something that you'd like to learn, I will give a plug to the Iowa Lego User Group if you like Legos. We meet every third Sunday at the Science Center. And yes, we have lots of adults. James is coming now. He's a member. So we have kids. We put out the brick every time. And then you'll get to see a lot of neat construction of what we do. So thank you.
Today I learned a lot about energy efficiency and how we need to build more high-performance buildings. I really liked the experience of building Legos and how when building highest towers, you know, different structures can build the sustainability of a building and how maybe the square isn't the best shape for a building. The presentation was really fun. I liked that he incorporated the Legos. That was very new and exciting, more interactive for us students to learn more about energy efficiency in buildings.
Well, we learned a lot about energy and sustainability with buildings. We learned how shading and different ways to utilize glass can affect different things about heating and cooling and lighting and how it all works together in the big puzzle and can make energy more useful and yeah.
Well, today was fun and interesting. I liked learning about the different energy efficiencies and what it was all about and taking it into perspective through the different buildings that I will be helping with and through future projects. So So it was fun kind of messing around with the Legos, very childish, but also fun and entertaining to see how to create new structures through simple tasks and making sure that you get all the design constraints in as well. So, yeah.